Okay, physics and measurements. Like all other science, physics is based on experimental observations and quantitative measurements. The main objectives of physics are to identify a limited number of fundamental laws that govern natural phenomena and use them to develop theories that can predict the results of future experiments. The fundamental laws used in developing theories are expressed in the language of mathematics, the tool that provides a bridge between theory and experiment. When there is a discrepancy between the prediction of a theory and experimental results, new or modified theories must be formulated to remove the discrepancy. Many times a theory is satisfactory only under limited conditions. A more general theory might be satisfactory without such limitations. For example, the laws of motion discovered by Isaac Newton, 1642 up to 1727, accurately describe the motion of objects moving at normal speeds, but do not apply to objects moving at speeds comparable to the speed of light. In contrast, the special theory of relativity developed later by Albert Einstein, 1879 up to 1955, gives the same results as Newton's law at low speeds, but also correctly describes the motion of objects at speeds approaching the speed of light. Hence, Einstein's special theory of relativity is more general theory of motion than that formed from the Newton's laws. Classical physics includes the principles of classical mechanics, thermodynamics, optics, electromagnetism, developed before 1900. Important contributions to classical physics were provided by Newton, who was also one of the originators of calculus as a mathematical tool. Major developments in mechanics continued in the 18th century, but the field of thermodynamics and electromagnetism were not developed until the latter parts of the 19th century. Principally because before that time, the apparatus for controlled experiments in these disciplines was either too crude or unavailable. A major revolution in physics, usually referred to as modern physics, began near the end of the 19th century. Modern physics developed mainly because many physical phenomena could not be explained by classical physics. The two most important developments in this modern era were the theories of relativity and quantum mechanics. Einstein's special theory of relativity not only correctly describes the motion of objects moving at speeds comparable to the speed of light, it also completely modifies the traditional concepts of space, time, and energy. The theory also shows that the speed of light is the upper limit of the speed of an object and that mass and energy are related. Quantum mechanics was formulated by a number of distinguished scientists to provide descriptions of physical phenomena at the atomic level. Many practical devices have been developed using the principles of quantum mechanics. Scientists continually work at improving our understanding of fundamental laws. Numerous technological advances in recent times are the result of the efforts of many scientists, engineers, and technicians, such as unmanned planetary explorations, a variety of developments and potential applications in the nanotechnology, micro security, and high-speed computers, sophisticated imaging technologies used in scientific research and medicine, and several remarkable results in genetic engineering. The effects of such developments and discoveries on our society have indeed been great, and it is very likely that future discoveries and developments will be exciting, challenging, and of great benefits to humanity.